Hi everyone. Okay, one thing that's often overlooked in education is the nature of different knowledge types and the implications that these have for learning. Now it's important to point out that engineering consists of all the kinds of knowledge and practices that I'm going to be talking about in this video. But it's useful for us to identify what kind of knowledge at what point, because that can tell us more about what it is that the student's not getting. It also helps us design our learning opportunities more effectively if we know what is the base knowledge at this particular moment and how is the student working with it. It also helps us then decide more effectively on what kinds of technologies or resources we might use in terms of emergency remote teaching, learning and assessment. Now, we're going to use some concepts from the sociology of education to unpack what we mean by knowledge. Now, some of this may sound very theoretical, but there are two important concepts to grasp. This comes from Basil Bernstein. Now, Bernstein talks about vertical and horizontal discourses. Now, vertical discourse is simply formalized educational knowledge. It's everything that we work with in the spaces in which we work. And horizontal discourse is everyday knowledge. Now, the problem is that the requirements of higher education have changed tremendously. If you look at all of our graduate attributes, you'll see that all of those elements are in fact based on the principle of exercising forms of knowledge and kinds of skills or practices in relation to society or in relation to particular professional fields. That means that in our teaching, we are constantly moving between what we call vertical and horizontal discourses. So we build good citizenship and good professionalism through modeling, in other words, learning from a social environment, but it must be based on a fundamental understanding that's implied in vertical discourse. Now, in vertical discourse, we have different kinds of knowledge structures. Now, the first structure and the most important is what we call hierarchical knowledge. Now, hierarchical knowledge simply is the kind of knowledge where concepts build on each other and add consistently. Physics is our classic hierarchical knowledge structure, and the other natural science areas. So the definition here is this is a knowledge structure which attempts to create very general propositions and theories which integrate knowledge at lower levels. We talk about a subsumptive progression of knowledge over time, where new theories or concepts extend and integrate earlier ones. Now, think about Ohm's law, for example. Ohm's law subsumes, absorbs the behavior of electrons, the nature of different conductors, principles of resistance, and so on. And it's reduced at its simplest to V equals IR. The example in the graphic over there is just force, for example. Okay? Now, this kind of knowledge takes a really long time to build, and it's integrated fairly sequentially in the school physics curriculum. Now, learning here is about strong sequencing. Each element must be grasped before the student can move on. You need to teach these elements explicitly, and you need to mediate at every single stage. Hierarchical knowledge structures require tools like mathematics or symbols or language or objects to demonstrate principles which describe the behavior of the physical world, whether at a nano or micro invisible level or whether at a physical level or at a visible level. Now, learning time. These types of knowledge take years to develop conceptual grasp. Now, if base sequential concepts are in place, principles can actually be grasped fairly quickly, and the periods of learning can become shorter and shorter. So, if, however, in terms of challenges, if base concepts are missing, then different kinds of interventions are necessary. Things like extra classes or winter school or revision of principles. Note that some of these principles can be elicited through actual experience. Now, to demonstrate understanding, in other words, to represent this understanding of this kind of knowledge, students require the use of other types of knowledge. They need language, symbols, graphics. Now, if the student doesn't grasp the appropriate forms of representation, these must also be explicitly taught. And here's the big challenge. Because they may not have the tools or understand how to use the tools to express their understanding, we may get confused. Is it the concept they're not getting, or is it the tool they're not getting? And that's an important thing that we need to identify when we address learning challenges. Now, the second knowledge structure type is called horizontal knowledge. Now, horizontal knowledge structures, and this is according to Bernstein, and I'm quoting, consist of a series of specialized languages with specialized modes of interrogation and criteria for construction. What that means is that there are kinds of knowledge structures where the same type has different languages. And each language has what Bernstein calls an explicit conceptual syntax, which is capable of precise or relatively precise empirical descriptions. To put it very simply, let's look at Pythagoras. Now, the theorem of Pythagoras is a squared plus b squared equals c squared has an explicit conceptual syntax. You see a squared plus b squared equals c squared, and you recognize it as mathematics. And you recognize that it empirically describes the lengths of the sides of a right-angled triangle. Now, each of these kinds of knowledge structures have multiple languages, and each of the languages, look at algebra, geometry, and trigonometry, has its own organizing principles, and learning of each of the types is a little bit similar to the learning of physics in that each type has its own rules internally that build on each other. The difference here is that there may be a different language of the same type to represent the same knowledge. An algebraic linear equation, for example, can be represented using coordinate geometry, but each has their own rules of syntax. Now, learning in these kinds of knowledge structures is slightly different. Each language and its own principles need to be learned independently. Now, sequencing is not as strong as in hierarchical knowledge, but principles need to be explicitly taught. The more language is acquired, the easier the learning of a new one. These kinds of knowledge are all the problem-solving tools that we talk about. They are languages used to analyze, manipulate, and explain phenomena, whether they're physical or social. There are often multiple approaches to applying this kind of knowledge. These kinds of knowledge need time to acquire the masses of particulars, and they need time to practice a range of application scenarios. A lot of this learning can also be done independently. Now, the types here, in case I didn't mention this before, this is mathematics, but this is also economics. Each paradigm, it's also politics, and law. Each paradigm, each type has its own rules, has its own kind of language. The big teaching and learning challenge here is the time for multiple types of application. Tutorials are ideal for this type of knowledge, where time is allowed to practice a range of approaches to solving problems. The grasp of procedural principles for each approach is also very important. Here is where understanding the appropriate form of representation and the conventions of that specific language are essential, and they must be explicitly taught. Sometimes group work is ideal for this type of knowledge. Now, this takes us to the third knowledge structure. It's also called horizontal knowledge, but it has what we call weak grammaticality and verticality. Quite simply, social sciences are generally classified as having a weak horizontal knowledge structure. And that is because, and I quote again, the capacity of the theory to stably identify its empirical correlates is weaker. In very simple terms, the same word could be used in multiple different languages. The word function, for example, it's in maths, it's in programming, it's in sociology, it's in chemistry. And it actually takes on different meanings in those different contexts. So you would have to define in which context. Now, Bernstein establishes that weak horizontal knowledge structures progress by way of proliferation and redundancy. Okay? There's a lot of cutting and copying and pasting from different kinds of knowledge areas. It changes over time, sometimes really rapidly. Now, we see this in information communication technologies. This is at the heart of computer-based engineering practice. Here, you will see that the different programming languages, they borrow terms from each other. They borrow syntax-related elements from each other, but each one has its own kind of rules and laws, and there's a lot of redundancy. Working with these kinds of knowledge structures means you constantly have to refresh your knowledge base. You have to adapt to new forms. You need to respond to a different set of organizing principles. Here, we do not have strong sequential learning as we have in the other cases. And here, we have what's important is you would need to learn to apply these in multiple contexts. So, just to repeat, this is non-sequential accumulation of masses of particulars. It can be done very effectively independently. It requires access to a range of examples and comparisons. There are many variations or options for solving the same problem. You know, a combination of tools like mathematics, symbols, and language to analyze, describe, and manipulate social or man-made phenomena. These types of knowledge take time and resources, and ideally, students need access to the required resources on their own to be able to practice. And trial and error works really well here. The big challenge is time and tools. Students need flexibility with regard to pace. They acquire this kind of knowledge in many different ways and at different rates because they also draw on their own conceptions of what the purpose of the tool is and how it is that they actually learn. Application here requires the combination of other types of knowledge, language, symbols, graphics, and if a student doesn't grasp the appropriate forms of representation, these must also be explicitly taught. Now, this is just an example from my own research on what happens in engineering. What happens when you integrate the different kinds of knowledge structures? Now, this example, as you see, is probably relevant to all of us, although this is because of my focus in my PhD on mechatronics, engineering problem solving. The problem is that, as you can see, if you separate out the different kinds of disciplines, they have different kinds of rules, different kinds of learning that is required, different kinds of allocation of time and resources. Now imagine when we throw that project at a student and we're trying to identify, well, where is the student actually struggling? We might easily talk about, well, time management, or talk about their inability to write a report, or quite possibly their inability to apply a particular tool, like a software program or mathematics. But hidden beneath that, and the reason that I've covered these knowledge structures with you, you would have to really zoom in to be able to identify what exactly is it that students are not coping with. So now we may well ask, so what? All engineering is a combination of these three core knowledge structures. Most engineering education is about using tools and techniques while drawing on fundamental principles dictated by the laws of natural science to address specific socioeconomic, socio-technical needs which require informed and criteria-based decision-making. Now, obviously, together, the modules in a program are intended to accomplish this synthesis. However, in your module, all three knowledge structures are present to different degrees and in different ways. And if you understand the differences and the implied learning challenges, this can help you to make informed decisions about what needs to be done in face-to-face mode, what students can do independently, and what technologies might be appropriate and useful. Now, we're going to be looking at these in depth in later videos. But to summarize and just to point out some of the emergency remote teaching, learning, and assessment opportunities here. So if we look at hierarchical knowledge structures here, short concept videos are ideal. Examples of the same principle in different contexts, and of course, revision, reinforcement, and the linking of concepts. Now, when it comes to horizontal, strong knowledge structures, here we all know worked examples work really well. facilitated synchronous tutorial type sessions, because the sequencing of this knowledge type, even though there are different kinds of languages within the same type, because the sequencing is important, it doesn't help to reach a point in a problem when a student is working on a worked example and to have to delay the support that they need or the help that they need by a day or a week, such as handing in a tutorial, which somebody only looks at much later. Synchronous tutorial type sessions, whether online or face-to-face, are really best here. Practicing on different kinds of applications and problems with the different kinds of horizontal knowledge structure languages here is important. Group work can also really help. So if you've got a problem with facilitating in a synchronous fashion, allowing students to work and to practice in groups can actually overcome this. Now, in terms of the third knowledge structure, which is particularly applicable to programming, for example, and ICTs and various technologies, here, examples of application, in other words, our classic how-to videos, facilitated asynchronous Q&A type sessions are really useful here, because the student needs to have explored, experienced, worked through trial and error to come to some kind of conclusion about what it is they're struggling with. If you had an immediate demi type in a traditional tutorial support, the way in which the student's working with a particular kind of, let's say, program, might take too much time for the demi to actually, or the lecturer even, to give input. But if the student has had enough time to explore and experiment, and then can consolidate by saying, this is what I'm struggling with. That's why asynchronous type or forum type support is really ideal here. These kinds of knowledge, independent practice on multiple applications and problems. Time, of course, is ideal. But as I said before, we will go into examples of what kind of strategies to use in the later videos on opportunities for contact-based and opportunities for remote learning.